let's find the center of mass of the right-hand unit semicircle when the circle is centered at the origin. So we've got a semicircle like this, and the radius of this thing is 1 unit. Okay. Now, so here's the x-axis and here's the y-axis. So let's calculate the moments about the x and the y-axis. For the moment about the x-axis, remember what a moment is calculating is the tendency of this shape to tip to one side or the other. But this unit semicircle, it's symmetric about the y-axis. So if you cut out a piece of cardboard to this shape and supported it along the x-axis here, it would balance. So because of the symmetry of the situation, so purely by symmetry, we know that the moment about the x-axis has to be 0. Okay, so we don't need to calculate the moment about the x-axis. If we did calculate the moment about the x-axis, we would get 0, but we don't need to calculate it, fortunately. Okay, so now let's find the moment about the y-axis. Remember, the moment about the y-axis is, in general, it's the integral from a to b. If your region is bounded above and below by a graph, all that jazz, it's integral from a to b of your density times x times f of x minus g of x dx. Okay, we don't have a density, but we can figure out these functions. So integral, let's see, we're going to be integrating from 0 up to 1 in the x direction. So 0 to 1, rho times x times, so f of x is this top semicircle, but that's the square root of 1 minus x squared because it's the unit circle. And g of x is the bottom semicircle, but that's, so minus, the bottom semicircle is minus the square root of 1 minus x squared. Dx. Okay, so when we simplify this, we get integral from 0 to 1. We might as well move this row outside while we're at it. Integral of x times 2 times the square root of 1 minus x squared dx. And now we need to evaluate this integral. Fortunately, the stuff inside of this square root, right, this is sort of prime u substitution territory. So if we let u be 1 minus x squared, du is minus 2x dx. And we have an x and a 2. So we can move this minus sign to the other side. So minus du is 2x dx. So this now becomes rho times the integral. So I need to translate my bounds. When x is 0, u is 1. And when x is 1, u is 0. So integral from 1 to 0 of, let's see, this x, 2, and dx all go into minus du, and then the square root of 1 minus x squared is square root of u. Okay, so now we can integrate. Let's pull this minus sign all the way out to the front. Integral of square root of u is 2/3 u to the 3/2. We're going from 1 to 0. So minus rho times 2/3 times, now we can plug in 0, minus, and now plug in 1. 1 to the 3/2 is 1. And let's see, so simplifying this, the minus signs cancel, we get 2/3 rho. So there's the moment about the y-axis. Remember, the moment about the x-axis was 0. So I guess the last piece we need to find the center of mass of this thing is to know what the mass is. So the mass is the density times the area of that region. That region is a semicircle, so we could calculate the area using an integral, but it's half of a circle, half of a unit circle. So its area is 1/2 pi times the radius squared, and the radius is 1. So rho over 2 pi is the mass. So now we can write the center of mass. X x bar, y bar. Remember, x bar is the moment about the y-axis over the mass. That's x bar. Y bar is the moment about the x-axis over the mass. So moment about the y-axis was 2/3 rho. Mass was rho over 2 times pi. And then moment about the x-axis was 0, so the y-coordinate of the center of mass is going to be 0. Okay, so now we can simplify this thing. Let's see, the rows cancel. This 2 flips to the numerator, so 4 over 3 pi, it looks like, comma 0. Let's get a decimal approximation for that so we can see if it looks about right. So 4 divided by 3 times pi. So this is 0.424 approximately, not exactly, but so if we look up at our unit circle, so 0.424, right, 1/2, 0.5 is right there, so 0.424 is going to be about here. So there's the center of mass of this disk, 0.424, comma 0. And that looks about right. In fact, I think it should be a little further to the right than I have it, but it's pretty close. And one nice thing about this center of mass sort of situation is if the density is constant, our eyes are very good at approximating the center of mass. You just kind of have to imagine, if this were a sheet of cardboard, where would I have to support this to balance it? And this point looks about right. Incidentally, when the density, so you might notice that right here, the density canceled. It didn't matter what the density of this material was. And as long as the density of the material is constant, that always happens. So if rho is constant, then the center of mass is independent of rho. And in this situation, the center of mass actually, it has a special name because it's a property not of a physical object, but it's a property purely of the geometric shape that you're dealing with. And in that case, the center of mass is also called the centroid. So centroid. So centroid is just the center of mass if rho is constant, or equivalently if rho is 1. If any constant gives you the same center of mass, you might as well let the constant be 1. So if your density is constant, you'll often see the center of mass called the centroid instead.